Okay, so guys, today what we're going to do to wrap up chapter 10 is, or 10, we're going to talk about gas kinetics. Functionally, what this means, because you understand kinetic energy is the energy of motion, so kinetic means something that's moving. Guys, functionally what this means is we're going to take our mental model of gases, which in many instances are pictures, right? We talked about close your eyes, picture what a gas looks like. You got the particles, they're spread out. If you haven't done this yet, when we talk about gas kinetics, what we're really going to do is take our picture and turn it into a video. We're going to talk about what's happening as these molecules move. Specifically, guys, what we're going to do is this. We are going to go back and we're going to revisit Boyle's and Charles' laws through the lens of our mental model of gases. In some ways, this will be review because we've talked about it a little bit. We're going to solidify those ideas today. So remember, Boyle's law is the inverse relationship between pressure and volume. Charles' law is the direct relationship between temperature and volume. We're going to revisit those relative to molecules that are moving. Then, guys, to wrap up the day, we're going to unpack an idea. You may remember last year, so let's talk about this. Last year, do you remember when we talked about how we measure the speeds of molecules? How do we know how fast molecules are going? What do we use as a representation of that? Temperature, right? And so, guys, we said that temperature is a measure of molecular speed, and if you've got two substances and if they're at the same temperature, their molecules are moving the same speed. Do you remember that from last year? Because that's not actually true. Guys, you're going to find out that if you've got two substances at the same temperature, their molecular speeds are not necessarily the same. You'll find out that something else is the same, and then we'll talk about how their speeds vary from there. And then, guys, that concept is then going to take us into the ideas effusion and diffusion. And I'm going to share an equation with, so by the way, grab your equation sheets. I'm going to share an equation with you that's not on the AP test, but I am going to have you write it into your equation sheet. Well, if you want to, but I'll put it on the board for the test. So you'll see. All right, you guys ready to go? All right, so again, up front, we are going to take our static models and turn them into videos. So guys, when we talk about kinetic molecular theory, this is just a bunch of stuff you want to write down. So guys, when we talk about kinetic molecular theory, we're obviously talking about the theory of moving molecules. Theory is a horrible term though, guys, because this isn't a theory. It's not up for debate. This is kind of what this stuff does. So it goes like this. When we talk about this kinetic molecular theory, we need to make sure that we're all okay with some basic assumptions. So guys, I'm just going to lay these out for you. So guys, I think you're going to be really comfortable with assumption number one. When we talk about gases, we understand that gases consist of very large numbers of randomly moving particles. Typically, they are molecular. I guess helium would be an example of one that's not. So you may want to write particles, but typically gases are molecular. No, it's an atom and not a molecule. Yeah. Yep. You guys good with that idea? So really, I mean, each one of these, you just need to mentally go, yes, I'm okay with that. And if the answer is no, I'm not okay with that, let's talk about helping you get okay with that by asking and answering questions. So we're good with this, right? Okay, how about number two? The volume of gas molecules is insignificant compared to the volume that the gas occupies. We okay with that? Remember we shared a number, right, that we promised we'd never talk about? 0.1%. So guys, if you've got a gas in a container, at standard temperature and pressure, about 0.1% of the actual volume, well, 1.1% of the volume of the gas is actually stuff. The rest of it's empty space. So we okay on thought number two? Yeah. Well, but realize that if the container gets extremely small, either A, you can't have much gas in there, or B, it's no longer at standard pressure. Do you see what I'm saying? I mean, and so, yeah, so it would have to be either, if you've got a small container, either there's a very small fraction of a mole in there, or it's at a very high pressure, and then this doesn't count. Is that okay? Okay, then guys, number 3, gases don't exhibit intermolecular forces. You okay with that idea? And that's exactly the point. Guys, look to the left. These first 3 points are actually all the fundamental understandings of ideal gases. You may want, I don't know if you want to write that in as sort of a summary. But yeah, basically these first 3 statements are just saying gases are ideal. So they're all familiar. So now guys, let's go with assumption number 4. And if you've taken physics, you probably have a more robust understanding of what we're about to talk about. You don't need to understand it anything more than as superficially as this is going to be on the board. So we understand that these molecules collide with each other. And when collisions occur, energy is exchanged. You guys understand that, right? Anytime 2 things run into each other, energy is exchanged between those 2 bodies. Here's the rule. The energy, when these things collide, the energy that is transferred without loss. And there's a name for that. Those are what are called elastic collisions. That's the physics term that you don't need to know. I always think about just erasing it because you don't need to know it, but I figure I may as well just leave it to leverage for those of you that have taken physics and understand elastic versus inelastic. But understand you don't need to, so we're not going to dig into elastic, but go ahead. And that's exactly the application of that. So what that means is the average kinetic energy of these things doesn't change so long as the temperature doesn't change. So that's exactly what we're saying, that is when these things, when they hit, energy is only exchanged between the particles. It's not lost as heat, which means the molecules are not slowing down. Yep, that's exactly it. Okay, so imagine if you and I were walking down the hallway in opposite directions and I ran into you. Yeah. We're going to bounce off of each other. And so imagine that I was walking more quickly than you. So not only am I more massive than you, but I'm also moving faster than you, which means I have higher kinetic energy. So when we hit, chances are good you're going to get knocked back because I'm fatter and moving faster. So when we hit, you're going to accelerate, and I'm going to slow down. And so we could then figure out yours and mine's kinetic energy going in, and then if we knew your mass and velocity after, we would know our kinetic energies after. And what we would find out is that before we hit, we had more energy than after we hit. If you and I are the system, and if you knew my kinetic energy and your kinetic energy and we hit, when we come out, the sum of our kinetic energies will have gone down. Where did the energy go? It was lost as heat and sound. So that would be an shouldn't say it. So that's not what gas molecules do.
So gases, they hit, except there's no, I guess, quote unquote sound or heat.
Exactly.
And the energy is the same.
Exactly. Energy in is, so what's the take-home message from that? And the idea is that these gases are not cooling down, because temperature for right now is a measure of speed, and if 2 particles collide and if their net velocities, because their masses don't change, if their net velocities go down, that means they're cooling down. And so if this were not true, you would have a balloon of gas and it would always be leaking energy to the surroundings, and eventually it would cool down and contract and change. So we're just saying these molecules on average don't slow down.
So this doesn't really happen.
Well,
kind of ideal situation.
Well, but okay, so we're saying this does, but understand, what if this didn't happen? Well, then if we had a balloon, happy birthday, here's your balloon, that balloon would always be contracting because as the molecules hit, they would be slowing down, contracting, and the balloon. But it doesn't shrivel down because the molecules are slowing down. It slows down because it leaks. You're actually losing gas through the balloon. That's why it gets smaller. But understand, the place where this doesn't really fit in real life is that balloon is actually always absorbing energy back from the environment. The room is being heated by furnaces. And so the idea is that in the real world, when these molecules hit, they actually do lose a little bit of energy to heat, but that energy loss is being replaced from our artificially heated rooms. Does that make sense? So we're just going to pretend like this is the case. You guys good on that? Okay. Now, guys, moving along. Number 2, number 5, number whatever this is. The next assumption that we are going to make is that average kinetic energy is proportional to the temperature. And we should say specifically the absolute temperature. What does that mean, by the way, absolute temperature? Kelvin. It means Kelvin. So, guys, let me foreshadow what we're going to talk about at the end of the day today. So this is new information. So let's talk about what this means and what this doesn't mean. So what does it mean that the average kinetic energy is proportional to absolute temperature? Here's what it means. So as the temperature of a gas goes up, what is actually increasing given this statement? It's kinetic energy. Does that make sense? So guys, when a gas is hotter, its kinetic energy is higher. How do we experience that increased kinetic energy? Higher velocity. And I think this is the next, it should be. So guys, the idea then is this. At any given temperature, the molecules of all gases have the same average kinetic energy. And if you don't remember, guys, kinetic energy is equal to 1/2 mv squared. So I'll let you write it down and then we'll talk about what this does and does not mean. It's going to be in a minute, yeah. Yeah. Just a second. Let me take a swing at it explaining it before we do questions. You guys okay? Not quite yet. You guys good? Okay. So here's what we know this, well, here's what we should understand this means. So first of all, given this first statement, what that means is as the temperature of a gas goes up, its kinetic energy increases. Is that okay? Okay, now guys, thought number 2 is this, because now we're talking about comparing different gases. So imagine that we have a balloon of helium and we have a balloon of methane. Okay, methane's the stuff in the lighters, and helium, helium balloons. So guys, if we've got 2 balloons, one is helium and one is methane, if those gases are at the same temperature, what do we know to also be true about those samples of gases? They have the same kinetic energies. Average kinetic energies. But guys, what they don't necessarily have is the same speeds. And we're going to talk about that at the end of the day. So these are the 2 things that we can take away from this. 1, heat up a gas, its kinetic energy goes up. 2, no matter what gas you have, helium, hydrogen, butane, doesn't matter, no matter what gas you have, if their temperatures are the same, their kinetic energies are the same, that does not mean their velocities are the same. Can we say now why not? Because they don't weigh the same. And we'll talk more about that at the end of what we're going to do. Go ahead, Jake. Yep, and we're going to look at that in just a second. Yep. Which velocity is directional, right?
Yes.
So speed is how fast you're going. Velocity also has a direction, but they're interchangeable. Someone else was gonna. Are we good? Rachel, somebody? No? Okay. Are we okay with these ideas? Okay. So guys, here's what we're gonna do with this then. What we need to do now is we need to take these ideas of molecules moving, and we need to go back and reconnect them with Boyle's and Charles' law. You're going to find out Boyle's law is really straightforward. Charles' law is a little less necessary. But guys, in order to do this, we've got to make sure we're clear on this. And this is review. I don't think you need to write it down. But are we comfortable with the idea that the pressure of a gas is attributed to the molecules banging against the walls? Is that okay? Okay. So guys, with that understanding, we understand then that pressure is really the result of two variables. One is how hard the molecules hit, and then number two is how often they hit. Is that okay? You guys good with those ideas?
So, I don't know, make with this what you will. When I first saw you put pressure as a result of two variables, I thought of how big the molecules are and how fast they travel. But mass doesn't mean anything because the molecules are as little as
So here, okay, I know mass does matter.
Okay.
And I don't want to go too crazy with this, but if we've got piv nert, we've got a mass factor here, and if we've got the same number of molecules and they're less massive, then the number of moles will be higher, which means the pressure is higher. So there is a mass component to this, but the reason that we don't think about the mass component is because we're not talking about comparing two different gases. We're saying, here's a gas. What could we do to it to change its pressure? And we're not saying replace it with a different gas that has a different mass. We're saying if you've got a gas, what could you do to that to change its pressure?
And you're answering that by saying, well, make the gas actually hit the container harder.
Exactly. Or
make it the molecules go faster.
exactly. And so now, but that's where this is headed. So the question then, guys, is if you've got a gas and if you want to change its pressure, what can you change about the gas to change its pressure? Well, the answer is you can make the molecules hit harder or softer, or you can make the molecules hit more or less frequently. So those are your two answers. You mentioned speed. That's where this is headed. Are you okay with the idea? So guys, what do you need to be able to do with this? Well, guys, consider, for example, this question. So, predictively, I want you to think through this. So you've got a gas, and if you make the volume bigger, okay, but the temperature doesn't change. If you've got a gas and you make the volume bigger without changing the temperature, what happens to the pressure and why? But I want you to think about this, because these are the practical applications of this that you need to be able to think through. So you've got a gas, you make the volume bigger. What happens to if temperature doesn't change, what happens to pressure and why? Think about it. And then we'll talk about it. So let's talk about it. First of all, guys, let's establish our hypothesis. If volume goes up without temperature changing, what happens to pressure? It goes down, right? But guys, now the question is why. And so in order to answer the why, let's go over here to our super picture, which I can't manipulate without getting out of presentation mode. But guys, the idea is this. And this should be a video. That would be cool. If I could make a video and then, I don't think it'd work. Anyway, okay. So guys, we understand these molecules are moving, right? And in order for them to exert a pressure, they've got to hit the sides of the container. And we understand that that pressure is attributed to how hard they hit and how often they hit. So you are all saying this. It sounds like we had a unanimous consensus on this, that if we make the balloon bigger, the pressure goes down. Are we all in agreement on that? The question is why? What is changing about the collisions with the wall that makes the pressure go down? Go ahead, man. No, I think you're saying it well. Keep going.
It's just like they don't.
You going to phone a friend?
Yes.
Who do you want to phone? Mark.
So we're saying all the molecules inside that are traveling at the same speed.
Okay.
Because they're all the same molecule.
You're going to find out in a minute that's not exactly the case, but keep going. So they have a speed.
They have a speed. If and that speed stays the same, if we expand the container.
Okay, hold on, time out. Guys, we got to talk about this. So Mark is saying that as we expand the container, the speed doesn't change. What in the question tells us that that's true? The temperature is not changing. If it didn't say no constant temperature, then that wouldn't necessarily be the case. But constant temperature, just a second, means no change in speed. So now what?
It means that there's more distance to travel to hit the side of the container.
Okay.
But since they're going at the same speed,
Right.
it's happening less
It's happening less frequently, yeah. Which, Matt, I think is what you were getting at. I think about it not as a distance issue, but as a proportion. We have a fixed number of molecules, and if those molecules are banging against a small surface area, they'll bang more frequently. When our surface area increases because we have the same number of particles, our particles have more, if you will, surface to cover, and therefore in any particular area, they're banging less frequently, and the pressure goes down. Is that okay? Go ahead.
So constant temperature also says, this probably sounds really obvious, but constant temperature also means there's no acceleration.
Yes, because if the temperature changes, they're being either accelerated or decelerated.
Yeah,
Yes.
and which is why this statement you just made holds true, because if there's no speed change, then they just have to move farther at the same speed.
Which is what Mark said.
Yes.
Yep, exactly. Okay, so guys,
But the magnitude of their hitting wall doesn't
and
change.
that was the question that I wanted to ask. So guys, let's summarize then. So when we're all in agreement that when the volume goes up, the pressure goes down, and now we're talking about why, and what did we say changed? Does the magnitude of the collisions change? How do we know? Because they're not moving any faster. The temperature is not changing. So it's not the magnitude of the collisions, it's the frequency of the collisions, and the frequency of the collisions are going down. Does that make sense? Whether you want to think about it the way Matt explained or Mark explained, guys, understand that the frequency of the collisions is going down, so the pressure goes down. Is that okay?
I'm just thinking, like, there's so many different ways to, hit nerve.
Yeah, exactly.
Or, pressure is force over area, say you're...
Right, exactly. So, and guys, that brings up a really interesting point, and you're going to get frustrated with this on the test and on the AP test, because did you hear what Jake said? He's like, there's so many different ways you could come at this, and I love that your thoughts were actually mathematical. Guys, you're going to run into this on the AP test where you're going to get to questions like this, and you're going to be asking yourself, should I handle this with mathematical equations, or should I handle this conceptually? There isn't a right answer to that. You could do this mathematically, but if you're going to do it mathematically, the problem is, remember guys, math equations only describe things, they don't explain things. So you couldn't say something like, in PivNerd, if T doesn't change, and if V goes up, P goes down. Because guys, gas molecules don't know how to do math. They don't understand that, so you're still going to end up having to explain it. Because the question will say explain, not describe. And when you're explaining, you've got to tie it back to the underlying principles and not just say in PivNerd, if V goes up, P goes down. That doesn't work. So my suggestion on these is if they're not asking you to do math, don't rely on math. Because if you're going to try to do math, you're still going to have to explain it conceptually. You know what I'm saying? Okay, so guys, this is an interesting final thought. What law does this represent? We just talked about the inverse relationship between volume and pressure. That's Boyle's law. Guys, this is Boyle's law conceptualized. They work opposite of each other so long as the temperature is not changing. Is that okay? Okay.
If you were to ask, volume increases at constant temperature, what happens to pressure and why? Could we have just gotten away with saying Boyle's law states this, and this.
You can't. You can't. You have to go back and explain, because the underlying reason it goes down is either the magnitude or the frequency of the collisions, and you've got to go back to that. Okay? You guys okay? Let's try one more. So what about this? We increase temperature at constant volume. What is going to happen to pressure, and again, why? So again, temperature goes up, volume doesn't change. So let's skip over here to our picture. And guys, if this is our picture, remember we said temperature goes up, volume doesn't change. So how does our picture change given the change that we're talking about? What's going to happen? What am I going to change? Nothing, right? I'm not going to drag this because it's constant volume. So now it becomes a mental imaging thing. So how is your picture changing given what we're talking about? These molecules are moving faster. So if the molecules are moving faster, what will then happen to pressure? Will it go up or down? Pressure will go up. And guys, why does pressure go up? Is it a frequency or a magnitude issue? It's a magnitude issue. Good, it's both. Do you see it? Because guys, it is a magnitude issue because they're hitting harder, they're moving more quickly, but why is it also a frequency issue? They're moving faster and therefore they're covering more ground, if you will. And so it's both a frequency and a magnitude issue. Does that make sense? Greater pressure changes? Kind of more bang for your buck because you're getting both a frequency and a magnitude increase. Yeah.
Is that true? Like, does it work mathematically? We'll get more change in pressure by increasing temperature?
Yeah. And realize that ties back to what you learned last year, and this might be a little bit of a stretch about reaction rates. Remember, because it's not just pressure that depends upon frequency and magnitude of collisions, it's also reaction rates. It's kind of a related idea. We'll go back to it in the next unit. Were you gonna? That's interesting. Interestingly, let's go back here, right? Because it's not. So let's talk about that. Yeah, because Charles is temperature and volume. And so this is not Charles' law. So what is it? Well, we can actually bring in the P. So we've got the combined gas law, right? P1, T1, V1, P2, V2, T2. And we are not talking about a volume change, so this is gone. So this is actually representative of pressure-temperature relationships, which actually doesn't have a name. It doesn't have a law. But if we look at before and after, we can see that if the temperature goes up, the pressure will also go up from the mathematical relationships in the equation. So it doesn't actually have a name, but we can still describe it mathematically, but we're hesitant to do that because we only want to go to the math if we need to. Okay. You guys good? Are we good on these connecting ideas? All right. So now, guys, drawing dots. We're going to shift gears. It's now finally time to actually talk about this idea of if temperature does not actually tell us speed, what does it actually tell us? So guys, last year, because it was general chemistry and I didn't want to hurt anybody, we talked about the idea that temperature is a measure of speed, hotter things go faster. Fundamentally, that's the case. But guys, this breaks down when we start talking comparatively. And we actually talked about this last year where we said if you have samples of two gases and if they're at the same temperature, their molecules will be moving the same speed. And that is not true. So guys, what is true? Well, here's the deal. Write down what you need. First of all, let's talk not about comparing gases. And you got to understand this subtle difference. We are not comparing one gas to another. We are looking only at one gas. So guys, if you're playing along at home, this is what we're talking about. Oh gosh. This is what we're talking about. So first we're going to look at one gas, red gas. So here, and I'll take you back to the notes in a minute, but let's set the stage very carefully. We're talking about red gas. We understand that these molecules are moving. Can we make them move faster? What do? Heat them up. Can we make them move slower? What do? Cool them down. But guys, the first thing that you've got to understand is this. All of these molecules are at the same temperature, right? They're in the same sample of gas. So this gas has a temperature. That does not mean that all the molecules are moving at the same speed. Just a second. Let that sink in, guys. When you measure the temperature of a substance, you are not, whether it's solid, liquid, or gas, but we're talking about gases. When you measure the temperature of a substance, you are not measuring the temperature of any particular particle or the speed of any particular particle. What you're actually doing is measuring an average temperature of the entire sample. Because guys, in a sample, and it doesn't matter if it's gases or a thing of water, it doesn't matter what you're measuring the temperature of. All the things in that sample are not moving the same speed. Some are moving faster, some are moving slower. When you take the temperature, you're taking the average of all of those speeds. So let me say this, and then Jake, we'll look at your question. So guys, this is then that idea in sentence form. While the molecules of a gas have an average kinetic energy, and therefore an average speed or temperature, not all the molecules in a gas, guys, are traveling at the same speed simultaneously. So if that's the case, what's actually going on? Well, guys, at any given time, some of these molecules are moving faster than the average. Some of these molecules are moving slower than the average. And when you take the temperature, what you're actually doing is measuring the temperature or speed of an average molecule. And some are moving faster and some are moving slower. Let me let you catch up in the notes, and then we'll talk about it more, and then we'll show you pictures. But I want to make sure that you're all at least connecting with the point here before we explore your questions. So fundamentally, guys, what we're saying is this. If you have a sample of a substance, be it solid, liquid, or gas, but we'll talk about gases. If you have a sample of gas, and if you could measure the speeds of all the particles in that sample, they are not traveling the same speed. Some are moving faster, some are moving slower, and we talk about averages. Are you guys all okay signing off on that idea? Okay, there's one more thing I need to mention to you that's not in the notes, and then we'll talk about it. So guys, can I go away from this? Okay, so guys, the idea then, what we're saying is this, that if we look at this sample of gas, and if we had like a little molecular speed meter, maybe this is a fast one, this is a slow one, this is a medium one, here's another fast one, here's another slow one. So guys, they are not all traveling the same speed. But the other thing that you need to be aware of is not only are they not all traveling the same speed, their speeds change. Why would their speeds change? What would cause them to change? Collisions. So guys, if you have a fast one collide with a slow one, the fast one slows down and the slow one speeds up. So their speeds are closing in on one another. But guys, understand they never become the same. When they collide, fast goes slower and slow goes faster. But they never all become the same. And so when we look at temperatures, it's actually an average speed of an average molecule, given that they have a range of different speeds or velocities. So that's what you need to understand. So let's answer questions. Go ahead.
It's like having a group of students in a classroom.
Okay.
Some will learn faster than others, but they're all in the same, I guess, circumstance. Yes?
Yeah, I see. I mean, I don't know that that analogy runs out well if you continue to dig into it. But you're right, that in a sample of students, some are faster or slower learners. Yeah, so that would be the case. Yeah, yeah. So, and so maybe in as much as that's true, Brendan, we understand that and this is universally true. You learn this from Gilchrist. Anytime you look at a population, we'll always have an average and we'll always have outliers. And that could be in learning or anything else. Because this really, that is, and so in that case, that's true because we're looking at populations. That's true. Go ahead.
So when I'm comfortable with this. When I get my mercury from, put that my 50 degree cold water.
Right.
Is that, like, how do I know? But how do you? What's going on? Is that the molecules are bumping into that thermometer?
Yeah.
Heats up a little bit.
Yeah, so what happens is, oh, that's not what I wanted to do. Well, it's half of what I wanted to do. So how then does a thermometer work? Whether it's mercury or digital, doesn't matter. So what we've got going on here is, say, let's just do water. Let's do water. So we've got particles in here, right? And then we've got our thermometer, which is functionally just a closed tube. And then in the bottom of it, we've got the mercury or whatever it is down here. And so, yeah, this is all literally driven by collisions. So these particles are moving around, they're running into each other, and they're running into the glass. And when they run into the glass, let's say that this is hot water. It works in either direction, but let's just say it's hot. So the thermometer starts at room temperature. The water starts out hot. So these are moving faster. And we know that heat always transfers from hot to cold. So these hot particles collide with the glass. What do? They slow down. So when this hot water molecule hits the glass, the hot water molecule loses some energy to the glass. Literally, the water molecule slows down and that glass molecule speeds up. Then that glass molecule imparts some energy then to a mercury atom. The glass molecule gives energy to the mercury speeds up, the glass slows down, and these mercury molecules, as they speed up, go up, and we experience that as temperature. Understand that if this water were cold, the flow of energy would just go in the opposite direction. But that's exactly what's happening. But understand that some of these faster molecules that get formed inside the mercury don't necessarily climb. They can also then hand energy back out to the water, and eventually this entire system comes into equilibrium. So the temperature of the water, the temperature of the glass, and the temperature of the mercury are all at the same temperature, and that changing of temperature of the mercury causes expansion, in this case, or contraction, which we then measure as temperature. But it's all about populations and averages. So we've got an average speed of water, which becomes the average speed of the glass, the average speed of the mercury, and therefore the average volume of the mercury. So that's what's happening.
So, I mean, I guess we can't ever be 100% accurate with this because we don't know if there's a slower molecule. We'll have outliers.
Right. Well, and not only can't you be 100% accurate, I'm sure you picked up on this, taking the temperature of something changes its temperature. So the temperature of that water is actually hotter before you take its temperature because it's losing energy into the thermometer. So yeah. Right, yeah, exactly. Yeah. It goes backwards forever. Go ahead.
So, you have two gases that constantly.
Hold on, let's not do two gases yet. We're talking one gas now. We're going to go two gases in just a second. So and guys, please understand this. Everything that we've done up until now has been one gas. So in one sample of gas, we understand that some particles are moving faster, some are moving slower. Brandon, we haven't got to two gases is what we're doing next. Is that okay? Okay, go ahead.
If you know,
Nope.
if you isolate the gas long enough, eventually all the molecules go at the same speed, right?
No. Yeah, and that's what I want to show you graphically. I'm going to use that as my segue. Guys, Matt's question was really, really good. He said, eventually, shouldn't all the molecules be moving the same speed if you isolate it? And so isolation is important because then you're not gaining or losing energy from the surroundings. But guys, the answer to Matt's question is still no. And the reason is because our population is on the order of moles. And when you've got 10 to the 23rd of anything, you're never going to have all the collisions that need to take place for that energy to distribute perfectly evenly through the sample. So even in an isolated gas, you will always have faster and slower.
Even if you wait like millions of years?
It's not pertinent to the conversation, but you're still going to have a distribution. Okay, so guys, what I'd like to do then, wait a minute. Guys, what I'd like to do is I'd like to show you that distribution. This is the distribution. Don't draw this, but let's talk about what it means. So guys, first of all, familiarize yourself, because Matt, this is actually a graphical representation of kind of what you were talking about, or at least the answer to your question. So guys, familiarize yourself with what this graph is displaying. On the x-axis, we've got speed. And then on the y-axis, we've got the number of molecules within 10 meters per second of that speed. It's an interesting way of representing this, but it actually brings us back to the point that you guys are getting at. Let me be able, I think I can zoom in and draw. So guys, first of all, this is kind of, it's weird units, right? But let me show you what it means. So here's the idea. You're comfortable with the idea that the x-axis is speed, right? Okay, now guys, take a look at the fact that we've got two curves. What do these two curves represent? Hot and cold, red and blue. They did everything they could to help you see that. So guys, red is hot, blue is cold. So guys, first of all, let's touch on the sort of obvious thing. Which is moving faster, hot or cold? Hot, right? So guys, how do we see that hot is moving faster? Well, look at the peak of the curve. Guys, you'll notice that the peak of the hot curve is to the right of the peak of the low curve, or the cold curve. So we see that on average, hot things are moving faster than cold things because hot is to the right of cold and speed increases to the right. Does that make sense? You okay with that idea? Okay, now guys, and understand they wrote this out of the AP curriculum, but I still want to explain it to you because you're going to see it in college. And for those of you that have taken statistics, you may understand this. So guys, there's a thing, have you guys, if you're in statistics, have you done root mean averages? Okay, here's the scoop. If you didn't hear what Jake said when I first threw these pictures on the board, he said they are, and I just lost the term for it, normal. Yeah, so guys, you look at this, and it looks like this distribution is normal. Do you guys understand normal distributions? The bell-shaped normal curve. These distributions are actually not technically perfectly normal. You'll know, yeah, you can see it, right? They're skewed to the right. The population is skewed to the right. So because they're not actually normal distributions, you can't find the average by just adding up all the data sets and dividing by the number of samples. It doesn't work because it's skewed. So statistically, the way to handle this is you take what's called the root mean squared average. Don't worry about it. It's not in the AP curriculum anymore. But guys, that is actually what these points represent. So the highest point there is what's called the root mean squared average speed. Don't worry about it. You won't see it on our test. You won't see it on the AP test. I just wanted to mention it. It's the proper way of taking the average of a non-normal distribution.
So in this instance, what's the difference between mean and average?
We don't need to worry about it. So guys, what we do need to figure out is this. Thought number one, we can see whether we're talking about root mean squared averages or just the peaks of the curve, that the hotter is to the right of the colder, showing us that the hot's faster. Is that okay? Now guys, do you want to talk about that? Yeah, kind of, but the problem is that with finding average atomic masses, there are, what would that be? I'm thinking of what are asymptotes. With that, there are not asymptotes. There are some things that are, and there are some things that aren't. With this, there are limits in terms of, there are no limits in terms of what's possible, other than zero. And so it's not exactly this, but I understand what you're saying about weighted averages, and it's not a horrible way to understand it. The only thing you really have to understand, though, guys, is simply this. On average, hot is moving faster than cold. Is that okay? Now, guys, let's talk about this. What does it mean? Let me ask that differently. What do the peak heights represent? Exactly, which I really like the way Jake described that as frequency. So guys, notice what's happening here. So if we had a truly evenly distributed number of speeds, you could almost picture maybe if we had an equal number, so if the same number of molecules were moving at each one of these speeds, then guys, our graphs would kind of look like this. We've got some going this fast, some going this fast, some going this fast, some going this fast, some going this fast. So the height of the line represents how many are traveling at that speed. And if the distribution was equal, if we had 10 going this speed, 10 going that speed, the line would be horizontal. But you'll notice that it's not, that it peaks around the average. And what does that tell us? Well, it's representative of this idea that when these molecules collide, the fast is going slower and the slow is going faster, and they're progressively closing in on that average speed. And we see that because the number of particles traveling at any particular speed gets higher as we get closer to the average. So they are, in fact, closing in on the average, but Matt, you'll notice they're not all going the average. There will always be a distribution, even over time, but they are, in fact, closing in on that average, which we see in terms of the elevation of the curve. So let me summarize for you, and then let's answer questions. So guys, fundamentally, you need to understand two things. Hot is moving faster than cold, and the speed of the molecules, while they're not all the same, are closing in on the average, but we will always have a distribution of fast and slow. So with that said, what do you need to talk about?
So is the U the actual, so U is 100 degrees, like the red U is 100 degrees Celsius, and blue U is 0 degrees Celsius?
Well, no, so the red U is the average velocity. So let's just look at red. If you can actually take all of these points and find their weighted, back to Rebecca's thought, find their weighted average, which we call the root mean squared average, this would be their weighted average. for this particular, oh, I see what you're saying. Yes, for this particular substance, yes.
So what I'm saying then is like, it looks like, let's assume this is water.
Mm-hmm.
It looks like in water, the most frequent temperature, the most frequent speed is actually freezing.
What?
Right? Because if you look at the blue U.
No, I'm not going to go there with you. You and I are going to sit down and talk because I would not touch that with a 10-foot pole. Guys, you need to understand hot is moving faster than cold, and they're closing in on the average temperatures. You and I will talk later. Go ahead.
Why is the red one like farther spread out? I don't know. To me,
Yeah.
the one is like
Let's talk and understand that this doesn't fall to zero, but think about it this way. Hot is moving faster, right? And if you're moving faster, that gives you more options, right? And if you've got more options, there's more different things it could be doing, and therefore they do those different things.
As you get
Yeah.
closer and closer to absolute zero.
We're not going there, but it does close down. Do you guys understand the fundamentals? You understand hot's moving faster than cold. You understand that they close in on the average speed, but there's still a distribution. Okay, so now guys, we are going to bring in the idea of now, and Brandon, this is where your brain was going. We're now going to talk about comparing speeds. So now we're going to look at two different gases. We understand that within any particular sample of a gas, the molecules are moving at different speeds. But what now if we've got two different gases? What will be true of their average speeds? And guys, it goes like this. And you probably want to get this in your notes. If we have two dissimilar gases and they have the same temperature, they have the same average kinetic energy. Guys, make sure you can sign off on that. That's important. If you've got two gases, and when we say dissimilar, we mean different compounds, different types of particles, different elements or compounds. So guys, if we've got two gases and they are not the same gas, if their temperatures are the same, then their average kinetic energies are the same. You guys sold on that?
Okay. Volume, pressure, those things don't have to be constant.
That's correct. You guys good? Mark.
So, if the average is the same, if you added up each kinetic energy for every
Hold on, they don't just say average, the average what?
The average kinetic energy is the same.
Okay, we haven't talked yet about kinetic energy. The graphs that we saw were speeds.
That one right there, using what's up on the board.
Okay, I thought you were trying to tie this back to our previous. Okay, keep going.
Using what's on the board.
Okay.
Since that's the average, if you added up the kinetic energy of every single molecule, the total kinetic energy, would that also be the same?
No, the averages would be the same. The totals would not necessarily be.
Okay.
So if you have a blimp full of gas, that's got a lot more kinetic energy than a balloon full of gas. Yeah. Right, it's the same number of moles. You guys good on this idea? Now, here's the thing I think we already understand, but I want to solidify this for us. Guys, what about the average speeds? Are they the same? And the answer is no. If the temperatures are the same, the kinetic energies are the same. But because these are dissimilar gases, their speeds are not the same. I'm going to get rid of necessarily. That word sounds wishy-washy enough that it sounds like you've got a way out. So guys, we're getting rid of necessarily.
And that's another always, right?
So long as their masses aren't the same. You could technically have two gases with the same masses that aren't the same gas, but it's not likely. Okay, so guys, the question then becomes, which are moving faster, which are moving slower? So why is it true that you could have two gases that their kinetic energies are the same, but their speeds aren't? And we all understand the answer to why, right? What's the difference? The mass. So guys, if you don't understand what I'm talking about, check this out. So here's the idea. We've got two gases now, and let's call the one on the left helium, let's call the one on the right neon. Now, we've got to agree that these are at the same temperature. So if they're at the same temperature, what is also the same about these gases? Kinetic energies. So this kinetic energy is equal. This kinetic energy is equal to this kinetic energy. But which gas is traveling faster in order for their kinetic energies to be the same? Well, guys, it's at this point we need to realize it's 1/2 mv squared. Forgive me, I'm just going to stay with red. And 1/2 mv squared. So these are equal. But if they're equal, we know their masses are not equal. So helium weighs 2 grams per mole, and neon weighs 20 grams per mole. So if the neon weighs less, what has to be true of its velocity to give it the same kinetic energy as the heavy guys? Got to be moving faster. So guys, the helium will be moving faster because it's lighter, and the neon will be moving slower because it's heavier, and that allows their kinetic energies to be equal. Does that make sense? Then let's write it down. Hold on a second. So it goes like the, oh, never mind. So we got the equation. So, oh, no, we were okay. There we go. Okay. So do you guys want that in sentence form, or can you just, no, we're gonna put it in sentence form. Okay, so here we go. Yep. So I got to take that. Okay, so how can we say this? In order for kinetic energy to be equal at equal temperatures, lighter gases must be traveling at higher average speeds than heavier. So guys, is this like what you wrote down? It's probably assumed, yeah, but I don't think it's wrong to say it. You guys okay with the idea? Okay. So guys, with this said then, there's one application of this that you need to understand. They wrote it out of the AP test. Well, that's not true. You need to understand this conceptually. You will not be asked to understand describe this mathematically, but you still must know this conceptually. So here it comes. This is what is called Ram's law of diffusion. So guys, diffusion. The other side. I'll just hand you my notes in a minute. So guys, let's are you familiar with diffusion and diffusion? Okay, let me give them to you. So guys, diffusion is a gas escaping from a container through a small hole. Diffusion is the process of spreading out and mixing. So, for example, if you've ever seen putting a drop of food color in a bucket of water, that food color spreads out through the water. That is diffusion. Or if you, my daughter does this, she loves room freshener sprays. And it makes me wish diffusion did not happen. because she like goes up in her bedroom and just unloads. Tracy will tell you. She's probably seen this. Tracy's my next door neighbor. It's horrible. Jessica just gets up there and unloads this horrible like strawberry stuff. And instead of staying in her room, it diffuses through our entire house and we have to evacuate. So guys, diffusion is that spreading out that happens. And guys, by the way, why does diffusion happen? Entropy. They are moving to conditions of higher disorder and it just happens. Guys, that is not effusion. I'll show you effusion in a minute. Diffusion is just the spreading. And it happens because of entropy. But guys, here's the thing you got to understand. It doesn't happen at the same speeds. Stick with me, gang. It doesn't happen at the same speeds. It turns out that the rates of both effusion and diffusion depend upon molecular speed. But what does molecular speed depend upon? Mass. So guys, the idea is this. I'm going to pull the variables out of this because you really don't need to know. Finding again that limiting confusion is helpful for us. Okay, so guys, it's fundamentally like this. Since smaller molecules have lower masses, they have higher average speeds. Consequently, they will diffuse more rapidly and effuse more rapidly. So because that ridiculous strawberry stuff that my daughter sprays spreads out through our house in what feels like a matter of seconds, those strawberry molecules must have a pretty low molecular mass. Or it could have something to do with the fact that the heater and air conditioner grabs a hold of it and spreads it out through the ductwork, which makes me angry as well. You get the idea? Okay, so guys, all of this, the application of this that you need to understand, and again, not mathematical anymore, but I'm going to show you the math. All of this ties back to this equation, which is called Graham's law. I offered that maybe you would want to write it down on your equation. Don't worry about putting it on your equation sheet. I'll put it on the board during the test. I would feel comfortable giving you this on the test, but you won't see it on the AP test. But guys, here's what it says. It says the rate of effusion of gas 1 compared to the rate of effusion of gas 2 is equal to the square of their molecular masses. But notice that it's 2/1. Because heavier gases do this slower, it's an inverse relationship, so it's 1/2 and 2/1. This is what is called Graham's law. It says that the effusion rate of a gas is inversely proportional to the square root of its mass. This is just effusion. So guys, understand, you just need to know this conceptually, but I'm going to show it to you mathematically. We may bleed a couple minutes into that weird period between this class and Pride, and then I'll do Pride reports and we'll get out of here. But guys, I want to show this to you conceptually. So it goes like this. Let me get rid of this, dig into here, go here. Oh, you know what? You know what, guys? Actually, the web link that I had to the thing that I wanted to show you is dead. Let's do this. You can do the math without seeing this. When I see you Friday, I'll actually start there. It looks like that link has died. So guys, we'll when we grade homework, I'll show you the animation I wanted to show you. This is your homework for today.